Okay, example 3 for rate of change. The area of a circular wave is expanding after a stone is thrown in the water. At what rate is the area expanding when the radius is 10 centimeters? Now you're going to get a couple of questions like this in this chapter. They'll ask you at what rate is the surface area expanding, at what rate is the area expanding, at what rate is the volume expanding. So you have to get used to this kind of question, and it's pretty tricky. So the trick in this is to figure out what's really going on. So usually what happens is we're given position time functions. We're used to dealing with those. We dealt with those in example 1 and 2. And now we're dealing with area and radius. So how can we potentially relate this question to those ones? So at what rate is the area expanding when the radius is 10 centimeters? Well, if this was a position and time function, we can relate it as at what rate is the position changing, or at what speed is the position changing when the time is whatever, 10 seconds. Okay, does that help you kind of see it a little more clearly? So let's start by figuring out what the dependent variable is and the independent. So usually with a position time function, the dependent variable is the position. So at what rate is the position changing when the time is 10 centimeters? So the area is like the position and the radius is like the time. So the position in a position time function is the dependent variable. So the area in this question is going to be the dependent variable. And the independent variable in this question is the radius. Okay, so how can we make a equation for the area in terms of the radius? Well, since we're dealing with a circular wave, we know that the area of a circle is equal to pi r squared. Okay, and we can maybe rewrite this as a, the function of a in terms of r, is equal to pi r squared. Okay? So they're asking at what rate is the area expanding when the radius is 10 centimeters. So since they're asking for the rate at a specific point in time when the radius is 10 centimeters, they're not asking for what's the rate between two different radiuses. They're asking for it at a radius. We know that we're dealing with instantaneous rate of change. So we're going to have to deal with the slope of a tangent. Okay, so we'll deal with the difference quotient, the limit as h goes to 0 of, let's just write the general formula for now, f of a plus h minus f of a all over h. The limit as h goes to 0, let's write the notation corresponding to this question. So the area, and our a value is going to be when the radius, when the r is 10. So we'll have 10 plus h minus a of 10 all over h. Now remember that this a corresponds to this equation here. So let's do a of 10 plus h on the side. So a of 10 plus h is going to equal pi r squared. So this is like our r. So the r, we have to sub in 10 plus h for the r. So 10 plus h squared. Okay, so we'll have pi, and then in brackets, when we FOIL this, we'll have 100 plus 20h plus h squared. And then let's distribute the pi, which is a constant, inside the bracket. So we'll have 100 pi plus 20 pi h plus pi h squared. Now a of 10, right, we have to find out what a of 10 is. Plug in 10 for the radius here. So we'll get pi 10 squared, which is just 100 pi. Remember that the pi is just a constant term. So plugging this and this back into our difference quotient, the limit as h goes to 0, a of 10 plus h is 100 pi plus 20 pi h plus pi h squared minus a of 10, which is just 100 pi, all over h. Now notice how the 100 pi and the negative 100 pi cancel out. And after they cancel out, we could factor out an h from the remaining two expressions. So we'll have the limit as h goes to 0 of h, and then we'll be left with 20 pi plus pi h all over h. Then the h's cancel out. So we'll have the limit as h goes to 0 of 20 pi plus pi h. And then when we plug in 0 for h, we're just left with 20 pi. Now, let's figure out what the units here are. So remember, the rate of change is how much the dependent variable is changing per 1 unit change in the independent variable. So the dependent variable, the area, is going to be in centimeters squared because the radius is in centimeters, and then the radius is just in centimeters. So at what rate is the area expanding when the radius is 10 centimeters? Well, the area is expanding by 20 pi centimeters squared per 1 unit change in the independent variable, which is the radius, per centimeter. Okay, so let's do a quick recap of this question. So at what rate is the area expanding when the radius is 10 centimeters? It's a circular wave is expanding after a stone is thrown in the water. So first we got to figure out what the dependent and the independent variable are. So the dependent variable is the area, the independent is the radius. Then we make an equation relating the two. So it's just the area of a circle. So we're going to be using this function in our difference quotient. And we did some calculations on the side here for a 10 plus h and a of 10 because we're finding the instantaneous rate at 10 centimeters. And then plugging those values back in here, we did some algebra. The constants cancel out. Then we're able to factor out an h. The h cancels out of the denominator. And then we could plug in 0 for h. And we end up with 20 pi centimeters squared per centimeter.